Welcome to Maths with EJD. We are talking about numerical optimization techniques. Before now, we had considered gradient-based methods like gradient descent, Newton's method, and conjugate gradient method. Starting from this video, we'll be looking at derivative-free methods. So you know that the gradient-based methods are actually based on being able to get the derivative of functions. So here we're talking about derivative-free methods. Probably if we have functions that are not differentiable, or we just feel like using these methods, then we can do this. So we don't need to find any derivatives. So the first in the series will be the Nelder-Mead method, which this video is about. And in the next video, we'll be talking about the about genetic algorithms. Of course, as the name implies, this is based on the idea of evolution in biology. And afterwards, we'll be talking about simulated annealing, which is borrowed from the idea of metal cooling, simulated annealing. Okay. So, like I said, this particular one is going to be about Nelder-Mead method. Now let's go for it. Nelder-Mead method, which is a derivative-free method for numerical optimization. So the Nelder-Mead method, also known as the downhill, okay, also known as the downhill simplex method, the downhill simplex method. So I've taken care of simplex method under numeric linear programming. I have about 55 videos on that playlist, so you want to check that out. Also known as the downhill simplex method, is a popular optimization algorithm used for minimizing a scalar function in a multi-dimensional space. Okay. Um, it's a direct search method, meaning it does not require the gradient, and that's why it is derivative free. It does not require the gradient of the objective function, like the gradient based methods, right? Does not require the gradient of the objective function, of the objective function, making it useful for problems where derivatives are difficult or expensive to compute. So if you have functions that are not so easy to find their derivatives, or the derivatives don't even exist, uh, we can use the Nelder-Mead method for problems where derivatives are difficult or expensive to compute. Okay, so let's see how the Nelder-Mead method works. How the Nelder-Mead method works. Okay, so the method uses a simplex. No, we said it's downward hill simplex method. The method uses a simplex, which is a geometric figure with n+1 vertices in n-dimensional space. Okay. In 2 dimensions, in 2D, a simplex is a triangle. And in 3D, it's a tetrahedron. Okay, I think we talked about this in the introduction video. In 3D, it's a tetrahedron. The method iteratively, adjusts the positions of these vertices. So if you're looking for X and Y, for instance, so you're going to be given three positions on a graph, right, which you can work with, as you're going to see very soon. The method iteratively adjusts the positions of these vertices to explore the function space, always attempting to reduce the value of the objective function. Okay, so let's look at the steps involved here. So the first step is the initialization, as we have in most numerical methods. We have the initialization. So here, start with n+1 points. That is the vertices of the simplex, the vertices of a simplex. Okay, in the search space. Choosing arbitrarily, like an initial guess, right? Choosing arbitrarily or based on a starting guess. Based on a starting guess. Okay, so that's the first thing we do. Number 2 is ordering. 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 So the first thing is we evaluate the function at each of the n+1 points. And the next thing is to sort the points such that the worst point, which is the highest function value. That is the point that gives you the highest result because you are minimizing. So the highest function value is at the last position. And the best point, which is the lowest function value, that's the value that gives you the lowest value of the objective function. The lowest function value is at the first. So because it gives you the minimum value for that iteration. Is that the first, all right? Then we go for step 3, where we talk about the reflection. Reflection. So here you reflect the worst point, reflect the worst point across the centroid. The centroid is the average of the other endpoints. Okay, the average of the other endpoints. If the reflected point improves the objective function, it replaces the worst point. Okay, that's the third point, reflection. The fourth point is expansion. This sounds like a lot. So if the reflected point up there, if the reflected point has the best function value, try expanding further. In the same direction. To explore the function more thoroughly. Then step 5 talks about contraction. So your reflection, expansion. Now we talk about contraction. Contraction. So for contraction, if the reflection does not improve, the objective, so you perform a contraction, moving the worst point, closer to the centroid to reduce the objective value. Okay, then we also have point 6 where we shrink. Point 6, shrink. So if no improvement is made, in the previous steps, shrink all points toward the best point. And then step 7, of course, you repeat until you get what you want. Step 7, repeat the process. So repeat. So you continue iterating until convergence criteria are met. Part of the criteria could be that the difference in function values, is sufficiently small. Is sufficiently small. So how small it should be will be determined by probably a tolerance level we would have set. So we've done things like that a couple of times. Function values, the difference between in function values is sufficiently small, or the movement of points, the movement of points becomes negligible. All right, so let's talk about let's take an example to drive home the point. So, example, suppose we want to minimize the following simple function, that is f of x comma y, which is equal to x minus 3 raised to power 2 plus y minus 2 raised to power 2. Now, this function can be differentiated, so we can use any of the gradient-based methods for it. So, but we just want to use the derivative-free method on it. So here, let's apply the Nelder-Mead method to minimize it, starting from initial points 1, 1, 2, 4, and 4, 1. Like we said, right, this is XY. So this is two-dimensional. This is 2D because we're talking about X and Y. And as a result of that, the starting point is going to form a triangle, just like we said previously. So you see, if you look at this point now, imagine you have this, and okay, let me at least be a bit close to scale possible. So this is like 1, 2, this is 1, this is 2, this is 3, and this is 4 for the x-axis. This is origin, this is 1, this is 2, this is 3, and this is 4. So if you look at the function itself, I think it's going to be some kind of circle or so. Yeah, something close to that. Because normally a circle would be x minus 3. I mean, x squared plus y squared equals r. So this is going to be something very close to a circle. But to estimate the minimum point, so we have initial guess of 3 points which can form a triangle, and that is what the Nelder-Mead thing is about. So first of all, we have 1, 1. This is like point A. Then we have 2, 4. This is 2 here and 4 up here. This is point B. And then we have 4, 1. This is 4, 1, like this. This is point C. So you see that actually forms a triangle. Then, because this is 1, 1, this is 1, 4, or is it 2, 4? This is 2, 4, and this is 4, 1. So we are going to use this point now, and then we start we start the process, and we start cutting into the triangle as much as we can, and we may have to contract it, expand it, or shrink the whole thing depending on the kind of outcomes we get as we go on. Okay, so let's go ahead and talk about step 1, which I believe we've even started already. Step 1 is about initialization, where we have an initial guess. Initialization. So we have point 1. Point 1 is 1, comma 1. in the coordinate system, we have point 2, which is 2, 4, and you have point 3, which is 4, 1. So you see all this form a triangle in 2D. And why is it 2D? The 2D implies the fact that we're talking about x and y, and that's what the function is talking about, x and y. The function we're dealing with, which is this, talks about x and y. Okay, so that's the first step. So if you don't have that, you want to guess by yourself if you don't have it. So we now have to evaluate. We evaluate the objective function. Evaluate the objective function of this, the objective function at this point. So don't forget the objective function is x minus 3 squared plus y minus 3 squared, So that means we have for f11, we have 1 minus 3 squared plus 1 minus 2 squared. So 1 minus 3 is minus 2. Minus 2 squared is 4. 1 minus 3 is minus 1. Minus 1 squared is 1. So this gives 5 straight up. Then we have f of 2, 4. That is the second point as we have it here. So that is 2 minus 3 squared plus 4 minus 2 squared. 2 minus 3 squared is minus 1 squared. That's 1. 4 minus 2 squared is 2 squared. That's 4. And that gives us 5 again. And then we have the last point, f of 4, 1. That is 4 minus 3 squared plus 1 minus 2 squared. 4 minus 3 is 1. 1 squared is 1. 1 minus 2 squared is minus 1. Minus 1 squared is 1. And that gives us 2. So now, we have got this now. If you follow the steps, after evaluating at all those points, the next thing we want to do is sort. So we have to order. So evaluate the function at each of the n plus 1 points. We are looking for x and y. So we have 3 points because 2, we are looking for x and y. That's 2. Then add 1, you get 3. So sort the points such that the worst point, highest function value. So here now we have two functions that have the same value. Let's see how we order this. So with this now, we just come and say that so the sorted points are, the best of them is 4, 1, okay? Because that gives us the smallest value. So the best is 4, 1, which implies that f of 4, 1 is 2. So that gives us the best value. Now, the other two give us the same thing, right? The other two give us the same thing, but how do we decide? How do we decide what it gives? So in this case now, we take the middle value. The middle one would be the one with 2, 4. That implies that we have f of 2, 4, like we have up there is 5. Then the worst, we have 1, 1. Though the value looks small, but they give us the worst. They give us 5. So so it looks like we pick the two small values, giving us 5 as the worst. So, but normally if the numbers are quite totally different, then we'll just choose based on the values of the function evaluated at those points. So we have all of that in order. Now we go for step 2, which talks about reflection. Step 2 is reflection. So the centroid, of course, the centroid of a triangle is if you draw lines to bisect this, I'm not doing a great job there. Let me just try. So bisect and bisect. So this would be like the centroid. That's not too perfect. That's not perfect, but that's what the centroid looks like in a triangle, right? So for the reflection, I would say the centroid of the best 2 points, which is 4, 1, and 2, 4. 4, 1, and 2, 4. Their centroid, uh, that's 4, 1, and 2, 4. This is 4, 1, and this is 2, 4. So this is their centroid. So this particular value is the centroid of those two lines. So the centroid of the best 2.41 and 24, okay, is this. So it's the centroid is equal to, this is x, say x1, x2, y1, y2. So more like the median of the line. So we have x1 plus x2 divided by 2, then y1 plus y2 divided by 2. So that means the centroid will be 4 plus 2 over 2, then 1 plus 4 over 2. So with that, we have 4 plus 2 is 6 divided by 2, that's 3. 1 plus 4 is 5 divided by 2, that's 2.5. So that's the centroid of the best 2 points. So what we're going to do now is reflect. So now, reflect the worst point, 1, 1 over the centroid, So that reflection, the reflection point R is some maths. R equals, so we have 3, 2.5, which is the centroid of the best 2 points, plus now the reflection is going to be, instead of this now, we now have 3 minus 1. The worst points are 1, 1. So that reflection will be this one now plus 3 minus 1, 5, no, 2.5, 2.5 minus 1. That's what we mean by reflection. So that point plus the distance between the point and the worst point, okay, that's the idea of reflection. So, and from that, we simply get that, this is the same thing as 3, 2.5 plus 3 minus 1 is 2. 2.5 minus 1 is 1.5. So if we put all of that together, we have 3 plus 2, 5. 2.5 plus 1.5, that's 4, 5, 4. So the reflection is 5, 4. So that takes us to step 3, just like what we've been following. So step 3 now that we have reflected the point, so we evaluate the reflected point. Evaluate the reflected point. Okay. So if you evaluate the reflected point, that's f of 5, 4. So that means we have 5 minus 3, x minus 3 squared plus y minus 3 squared, that's 4, y minus 2 squared, that's 4 minus 2 squared. And that's simply 5 minus 3 is 2 squared, 4 minus 2 is 2 squared, and that is 4 plus 4, which is equal to 8. So f, 5, 4 is 8. So that value is bigger than even the things we got before, right? So we have to make a statement that since f of 5, 4 is equal to 8 rather, is worse than f, 1. So if you got something better than this, then the story will be different. Is worse than f, 1. Is worse than f, 1. S 4 of 4, 1 rather, which is equal to 2. Then we do not accept the reflection. So the reflection doesn't work in this case. Do not accept the reflection. So we proceed to a contraction. So if the reflection was better, we wouldn't need to move on to a contraction. So now a contraction is necessary as we go to step 4. So step 4 now, we now have a contraction. I mean, this is kind of tedious. So it looks like these direct methods may be more troublesome because we don't have derivatives for the functions usually. So the contraction point the contraction point, which is C, is found by moving 1, closer. I said closer. That's closer to the centroid. Closer to the centroid, which is 3, 2.5. So now let's use a contraction factor. So you can choose a contraction factor. Let's use a contraction factor, which is alpha equals 0.5, so that our C becomes 3, 2.5 plus 0.5 into 1, 1 minus 3, 2.5. So that's how that goes. So that C now is equal to 3, 2.5 plus 0.5 into 1 minus 3, that's minus 2. 1 minus 2.5, that's minus 1.5, I believe. Yep. Yes, that's how it is. So this is now 3, 2.5 plus 0.5 times minus 1, that's minus 1, times minus 2, that's minus 1. 0.5 times minus 1.5, that's minus 0.75. And we can operate this together. So 3 minus 1 is 2. 2.5 minus 0.75. 2.5 minus 0.75. That should be 1.75, I think. Yeah, 1.75. Is that correct? 2.5, 2.50 minus 0.75. So 10, this is 5, this is 4, 14, that's 7. Yeah, 1.75, that works. So that is what that looks like. So that's the contraction point now. The contraction point is 2, 1.75. So again, we are now going to evaluate. So we evaluate f of 2, 1.75. Okay. So that is f of 2, 1.75. That is equal to 2 minus 3 squared plus 1.75 minus 2 squared. Okay. So that is equal to 2 minus 3 squared. 2 minus 3 is 1. So 1 squared is 1 plus 1.75 minus 2. That is 0.25, I believe. So 0.25 squared is 0.0625, okay, which is equal to 1.0625. So that's the function evaluated at that point. So now this value is better than the best we've had so far. So we have to make a statement that since f of 2, 1.75 is equal to 1.0625 is better than f of 5, 4, which is equal to 8, then we accept the contraction. So the contraction works better. So we accept the contraction. So this is more like the first guess, x is 2, y is 1.75. That's like the first guess in this situation. So after this, we go to step 5. Of course, so again, we now repeat the process as usual. So repeat the process. How do we repeat? We now use 4, 1, 2, 4. That gave us the best results before. That gave us the first and second results, and this new contraction point. So if the reflection point was better, we would have used it. But since the contraction point is better, so we now knock off that last value 1, 1 and use 2.2, 1.75 as the new point now. So we now use this as the new simplex, I think it's interesting, except that it can be a bit long, as the new simplex, and repeat the steps until convergence. So the convergence here can be based on the function of f. So by the time you get to a point where the value of f is becoming like exactly the same every step, then yeah, you can see you have reached convergence, or the number of iterations can also be stated. So as a new simplex, okay, these are and repeat the steps until convergence. Okay, so adjusting points based on reflection, based on reflection, expansion, contraction, or or shrinking. So normally, right, we know all these three already. You remember 4-1, 4-1, what did 4-1 give us again? 4-1 gave us what's that? 4-1 gave us 2, 2-4 gave us 5. Okay. So 4-1 gave us 2, 2-4 gave us 5, and this gave us 1.0625. So from here now we can sort again, and then the worst will now be 2-4. Then we try to knock that worst one off, and then we keep iterating. But at this point, I mean, it can get very tedious. So what I'm going to do is, as usual, go to Python for some help. Okay, we go to Python for help. So here we are. For the Nelder-Mead method, we define the objective function, which is f of x, y equals x minus 3 squared plus y minus 2 squared. You know, that's defined here as what you see in line 5. Then we define the Nelder-Mead, which it takes the function we have defined. It takes the initial simplex, which is those three values, those 3 points in the triangle. Then we have alpha. We take alpha to be 1, we take gamma to be 2. Then rho is 0.0.5, sigma is 0.5, and all that. Then I mean you can study all this, it's a bit but plenty, but then you can sit with it and try to tweak and see what happens, so that at the end of the day we define the initial simplex here, which is necessary for the whole process, and then we click, and then in 26 iterations, right? In 26 iterations, we get a minimum point, which is 2.998 something something. That's roughly 3. And we get that's the value of x. The value of y is 2. So roughly 2. So this is roughly 3. This is roughly 2. And then when you come to the minimum value, it is 1.918 times 10 raised to the minus 6. That's 0.5 zeros before you get to 1. So that's almost zero, right? And then that happens in 26 iterations. And then if you look at the function we started with, you'll discover that the minimum point will be something like whatever will turn this to 0, most likely is the minimum point, because this function never goes negative. You know, because of the square, the function will never be negative. So the worst case scenario is to have it as 0. So that means for it to be 0, x has to be 3 and y has to be 2. Okay, so that can take us to the conclusion for the Nelder-Mead method, which is quite an interesting one. Let's talk about the conclusion in this situation now. Um, okay. Um, in conclusion, right? Conclusion. The Nelder-Mead method iteratively refines the search for the minimum. Okay, let me just write the Nelder-Mead, the Nelder-Mead method iteratively refines the search for the minimum by adjusting the simplex. So like we said, in 2D, the simplex is a triangle. In 3D, the simplex is a tetrahedron. By adjusting the simplex based on the objective, based on the objective functions values. Okay. In this particular example, um, in this example, the algorithm moves toward a minimum, near 3, 2, as we see, the function can never be negative because of the powers. So the worst it can be is 0. And 3, 2 is what gives you that 0. So toward the minimum near 3, 2, which corresponds to the global minimum, of the function. Okay. All right. So that helps with the Nelder-Mead method. So let's see if we can get some practice questions. Okay. So practice questions. Yeah, I mean, you can explain. I won't write this down. Explain why the Nelder-Mead method does not require gradient calculations. What is the role of the simplex in the algorithm? List the 4 main transformations used in the Nelder-Mead method. Of course, of dealt with things like reflection, contraction, shrinking, and all of that. Then 2, the algorithm application. Okay, let's see. 1, given the initial simplex points, 0, 0, 2, 1, 1, 3, apply one iteration, of the, you can go more than one actually to really test that your knowledge. Apply one iteration of the Nelder-Mead method to minimize f of x comma y equals x squared plus y squared. Okay. So if a function okay, this is one like 1a and this is like 1b. If a function has multiple local minima, how does the Nelder-Mead method handle them? The Nelder-Mead method handle them. You want to search that out? Okay. Okay. Guess I want to let me add a second one. 2a, compute the reflection point. Compute the reflection point for the simplex. I mean, you saw how we just did that. Now for the simplex, 1, 2, 3, 4, 5, 1. If the worst point is 5, 1. Okay. If that's the worst point, then B now, a function evaluates to f of f1, 2 is 5. That's the best point. Then you have f, 3, f3, 3, 4, right? F of 3, 4, that's 8. That's the middle point. Okay. And then you have f 5, 1. That's 12, which is the worst. Okay. So the question is to compute the new simplex. Compute the new simplex after one step of reflection. If the centroid is 2, 3, if the centroid is 2 comma 3. Of course, the centroid is 2 comma 3 because the first two, 1 plus 3 is 4, 4 divided by 2, 2, 2 plus 4, 6 divided by 2, that's 3. So that's the centroid. So, I mean, let me see this in the comment section. Let me see your efforts in the comment section as far as this is concerned. And of course, let me also know in the comment section how helpful these videos are for you. Then also, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then, if you have not subscribed, please go ahead and do that. If you have, thank you. And also, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then like and share so that more people can have access to this great learning. Till I come your way again, keep doing math right. Bye.